with Thomas Stark from the German Aerospace Center, and he will be talking on utilizing CNNs for classification and uncertainty quantification for 15 families of European fly pollinators.
Thank you very much for the kind introduction. Imagine you're near this beautiful meadow. Maybe you're on a hike and you know there are no project deadlines, no Python errors, no Zoom meetings. Maybe you see a little bee flying around and you think, ah, that's nice. Maybe you even take out your smartphone and take a picture of this bee when it's on the flower. Maybe you're even aware of some projects like iNaturalist or the Global Biodiversity Information Facility, GBIF, where you can upload the image you just took. And there you get some more information about the image that you just took. That in this case, the image of the beautiful bee that you just took is in fact a Western European honeybee. And you're not alone if you would do something like this. Only alone in Germany, there are more than 4 million images of bees and butterflies on the dataset of GBIF. But for flies, there are less than 730,000 images of them. But flies really rival bees in contributing to nearly 40% of the global crop pollination. And the importance of pollination is probably aware to everyone that nearly 90% of all plants rely on pollinators, making the decline of pollinators so dramatic. Now, I would like to take you on a small scientific journey that actually started at Helmholtz AI Conference in 2022, where a colleague of mine, Robin Spanier, did a talk on how we can use deep learning to detect pollinators. In this turn, we then used different object detection models to detect flower-visiting anthropods on online images, like from GBIF dataset. And then we went to the field using smartphones on tripods, collected a large data set of flower-visiting pollinators, and tried to use our object detection models without fine-tuning or transfer learning directly to this new image acquisition. So by now, we know that we can fairly reliably detect different orders of pollinators quite well. So what happens if we want to have a closer look at one specific order of pollinators, like flies? So the question is, can CNNs classify 15 different Diptera families? For this, we selected 15 European pollinating fly families, here sorted in alphabetically order with some example images, and we downloaded roughly 30,000 images from the dataset GBIF for each of these families. In addition, we also drew bounding boxes around each of the specimens themselves. We did this in a two-step fashion. So first, we used our previously object detection methods, and then two expert ecologists adjusted the bounding boxes to make them as perfect as possible for each of the 30,000 images. We did this so in order we could compare the original image sizes to the cropped images that are aligned to the full specimen of the pollinator. Then, from this data set, which we split in a stratified fashion, so training, validation, and testing data set, we selected 3 off-the-shelf CNNs, ResNet, MobileNet, and EfficientNet, and from the start, we kind of knew that there are a few families that share very morphologic similar traits. Here we can see the families Fanidae, Muscidae, and Tachinidae. And it's extremely difficult to differentiate between them. Sometimes the color of their hair is slightly different, the color of their body is slightly different, they have different wing patterns, but it's even difficult for ecology experts to differentiate between them. So it would be great if we would have a methodology approach that would be able to somehow estimate the confidence in the prediction that we can know if it's sure that this is an image of a Fanidae, for example. So we did this using Monte Carlo methods where we took 100 classifications of the same input image that are slightly different. So for each of the 100 classifications, we get a slightly different prediction y hat. We use a combination of test time augmentations and test time dropout, where the augmentations model the ambiguity of the input data and test time dropout models the uncertainty within the model parameters. So from these 100 slightly different predictions, we get a sample-based approximation of the Bayesian predictive distribution. And from this on, we can calculate the confidence of our predictions. But we can also compare the confidence results between the original images to the images that we cropped with the bounding boxes and compare them. Here in this table, we can see the results for each of the model, the number of parameters, the overall accuracy, the mean confidence, and if we use the original images or if we cropped the images to the bounding boxes. We can see that the larger the model is, typically we get higher results. When we focus on the overall accuracy, we can see when comparing the mean results for the original images to the images that we cropped, there's improvement of roughly 5.6%, and the mean confidence has a mean improvement of roughly 8.6%. Here we can see 3 predictions of crop images for the family of Fanidae. We can see that the first 2 predictions have a high confidence values, and the last image has a low confidence score of roughly 50%. When we compare this to the reference data, we can see that the first 2 classifications are correct, whereas the last one is a misclassification. So the low confidence score indicates this somehow, and it's not a Fanidae, but it's actually a Muscidae. Here we can see 3 classifications again for the family of Muscidae, where again we have high confidence scores for the first 2 examples and a low confidence score for the last one. If we compare this to the reference data, we can see the first 2 images are correct classifications, whereas the last one is a misclassification. It's not a Muscidae, it's actually a Tachinidae. And very similar, here we can see 3 classifications again for predictions of Tachinidae with high confidence scores of, for the first 2 images, and a very low confidence score of only 32% of the last one. And you probably all guessed it, the first 2 are correct again, whereas the classification with a low confidence score is a misclassification, and it's actually a Fanidae. So, using uncertainty quantification, we can not only improve the confidence of correct predictions, but probably more important, we can transparently highlight misclassifications as well. So there are a few take-home messages. Save the bees, yes, it's very important. Probably better would be save all pollinators, including flies. Monte Carlo uncertainty estimations are an efficient way to get confidences in classifications. It can help expose misclassifications, and in our case, it really helped distinguishing between morphological similar families. And lastly, next time you're on a hike or you're just walking around and you see a pollinator on the flower, I really encourage you, take a picture and upload it to the database of your choice, GBIF. It really helps biodiversity research. And with that, I want to thank you very much for your attention, and I'm happy to take any questions.
Thank you. Cool talk. And we have people lining up for questions. Go ahead.
Hi, thanks for the talk. It was very interesting. Just wondering, like, kind of with the uploaded images, because all the images you showed, they are like very high quality and beautiful and near shots and so on. So how do you work with the uploaded images if they're like very bad quality or resolution and so on?
Cool. So in this case, like in the beginning, I showed that there are like these 730,000 images of flies, and we only used like 30,000 of them from European flies even. So we really try to make sure to only get the good images, specifically of flies that are near flowers or have flowers in the background, because that's what we're interested in the plant-pollinator interaction. Many of the images on GBIF or iNaturalist are on museums as well, like where the specimen gets killed and then dissected. So there probably half of the data set is from museum images. So it was a data pre-processing step that we really try to make sure to get the beautiful images.
Follow-up, was it automatically done?
Since we have more questions, I'm sorry, but now I have to start cutting follow-up questions, and we will go to the back.
Well, thanks for your efforts for also assessing uncertainties with the predictions. I was wondering, I'm not sure if I completely got your method, but would your way of estimating uncertainty also work if you don't have the ground truth labels?
Probably yes. I mean, it's just like if you take a pre-trained CNN and then do like incorporate test time dropout and test time augmentation, you would get a sample